Hello, and welcome to this lecture in my series on the satisfiability problem for fragments of first-order logic. My name is Ian Pratt-Hartmann, and today I'll be talking about the Gödel fragment. I'll be showing that the satisfiability problem for the Gödel fragment is decidable, and I'll establish an upper complexity bound. As usual in these lectures, I shall assume basic knowledge of first-order logic and complexity theory. I'll be explaining the main ideas behind the proof, but I won't be going through everything line by line. If you want to do that, then I recommend the text shown here on the slide. First, we need to define what the Gödel fragment is. A formula is in pre-nex form if none of its Boolean connectives outscopes any of its quantifiers. In other words, if all the quantifiers are at the front. For example, the formula you see here, every student with a degree is a graduate student, is a pre-nex form formula because the quantifiers are all at the front, two universal quantifiers. It's a standard result that every first-order formula is logically equivalent to one in pre-nex form. For example, here's a formula. It says essentially the same thing. For all x, if x is a graduate student and there exists x2, since x2 is a degree and x1 has x2, then x1 is a graduate student. You see the quantifiers aren't all at the front, so it's not in pre-nex form, but it's logically equivalent to the first sentence we started with, and this is true quite generally. Every sentence of first-order logic is equivalent to one in pre-nex form. You can always move the quantifiers to the front. The quantifier prefix of a pre-nex form formula is the word over the alphabet for all there exists, formed by its quantifiers. So for example, in this formula here, the quantifier prefix is for all. So that's a two-letter word over this alphabet. Now, any set W of quantifier prefixes defines a fragment of first-order logic. The formula is in pre-nex form, having a quantifier prefix in that set W. Usually, W is specified as a finite word over the four-letter alphabet for all there exists, for all star there exists star, where star means any number of occurrences of, including 0. So to take our example here, this sentence has quantifier prefix for all. So that is in any of the words, well, that's certainly described by the words for all. It's also described by the set of words there exists star for all there exists star, because we have, in this case, no existential quantifiers, two universal quantifiers, no existential quantifiers. And it's also in the set of words for all star, which is any number of universal quantifiers. And in this case, we just have two. So, for any word W over for all there exists, for all star there exists star, we take W, subscripted with equal in square brackets, to be the set of function-free first-order sentences in pre-nex form with a quantifier prefix described by the word W. Similarly, we take W in square brackets but without the equality subscript to be the set of function-free, equality-free first-order sentences in pre-nex form with quantifier prefix described by W. And we employ exponent notation in the usual way. Thus, exists star for all squared there exists star just means the same as there exists star for all there exists star. That's just an abbreviation. So, the example formula we started with, the sentence for all x1, for all x2, and then this quantifier free part here, is in the fragment square brackets for all squared, because we have exactly two universal quantifiers. And it's also in the fragment square brackets there exists star for all squared there exists star, because that is the set of pre-nex form formulas with any number of existential quantifiers, two universal quantifiers, and then any number of existential quantifiers, including the number 0, which is what we have in this case. So finally, we allow individual constants in quantifier prefix fragments, but no function symbols. And whether we or not we allow equality depends on whether we have this equality subscript. That turns out to be important. It was realised in the early stages of research into the decision problem, or the Entscheidungsproblem, that some quantifier prefix fragments have decidable satisfiability problems, while others don't. Here is an example here are 3 examples of quantifier prefix fragments for which the satisfiability problem is decidable. The first is the so-called Bernays-Schoenfinkel class, and that is the class of formulas with quantifier prefix fitting the pattern there exists star for all star. In other words, any number of existential quantifiers followed by any number of universal quantifiers, but you can't have any existential quantifiers following a universal quantifier. And we allow equality. So it's very easy to see that the satisfiability problem for formulas in that class is decidable. The same goes for the Ackermann class. It's a little bit harder to see. So we have any number of existential quantifiers, a single universal quantifier, and then any number of existential quantifiers, and we allow equality. And again, the satisfiability problem for formulas in this class is decidable. And the class we'll be talking about today, where we have 2 adjacent universal quantifiers flanked by any number of existential quantifiers, the so-called Gödel class. And here we do not have equality. That's quite important. Here are some quantifier prefix classes which are undecidable for satisfiability. If we have 3 universal quantifiers, then the satisfiability problem is undecidable. If we have 2 universal quantifiers but an existential quantifier in between, then again, satisfiability problem for such formulas is undecidable. And if we have 2 universal quantifiers which are together, but we also have equality, existential quantifiers either side, and we also have equality, that class again is undecidable. So if we add equality to the Gödel class, we get an undecidable fragment. So in this lecture, I'll simply be talking about the Gödel fragment, and that's I'll show that the satisfiability problem for this fragment is decidable. Okay, remember that's the fragment of formulas in pre-next form where the quantifier prefix has any number of existential quantifiers, 2 universal quantifiers, and any number of existential quantifiers. Okay, so now we know what the Gödel fragment is. Remember, these formulas are function-free and there is no equality. Here's an example of perhaps another example of a formula in the Gödel fragment might be useful, one with some existential quantifiers here. So no lecturer introduces any professor to every student. That's in the Gödel fragment. We have 2 universal quantifiers, an existential quantifier, so it's definitely in the prescribed form. There's no equality, and I think you'll agree that that formula is glossed by the sentence above. Okay, and I've already stressed equality is not permitted. Okay, so the next observation, the Gödel fragment's effectively closed under conjunction. It's not completely obvious, but it's not too difficult. So suppose you have 2 formulas in the Gödel fragment. So here's a blue formula. There exists x bar, so x bar is any tuple of variables. For all y1, for all y2, there exists z bar, and then some quantifier-free rump here. So, and then the second conjunct has essentially the same form. If we take the conjunction of those 2 formulas, it's fairly easy to see that this is logically equivalent to the formula written below. And all I've done is I've taken all the quantifiers to the front. I've kept the universal quantifiers the same, but I've renamed the existential quantifiers in the second formula. I've renamed x bar prime to x bar double prime, and similarly with z bar prime and z bar double prime, and you can convince yourself that these two formulas are logically equivalent, and you'll see that this second formula is in the Gödel fragment: existential quantifiers, two universals, existential quantifiers, and then the rest is quantifier free. Okay, so that's the. So if we are interested in determining satisfiability for sets or finite sets of formulas in this fragment, well, that's just the same as determining satisfiability for single formulas. So that's what we'll concentrate on in the sequel. Now, if phi is a sentence of the two-variable fragment, which we talked about in a previous lecture, and phi does not contain equality, then we can compute in polynomial time, actually in logarithmic space, a sentence psi also in the two-variable fragment, which has this form. So this is so-called Scott normal form. We have two universal quantifiers and then a quantifier-free formula alpha, and we have then a conjunction of formulas, each of which starts with a universal quantifier, an existential quantifier, and then has a quantifier-free part, beta h. And these alpha and beta, of course, equality-free. And if you manipulate the quantifiers very slightly, you have to rename these variables, as I did on the previous slide, more or less. You can write the formula in this form. So we have for all x, for all y, there exists x1 up to there exists z1 up to there exists zm, and I've just substituted the zh's for the y in here. And so it turns out that this second formula here is logically equivalent to the first formula, and every formula in the two-variable fragment can be transformed into an equisatisfiable formula of this form. So that gives us a reduction from the two-variable fragment to the Gödel fragment. So in fact, being able to solve the satisfiability problem for the Gödel fragment ensures that we can solve the satisfiability problem for the two-variable fragment, at least without equality. Now, in a previous lecture, I showed that the two-variable fragment with equality is decidable for satisfiability, but with the version of that theorem without equality follows from what we'll be talking about today. I mentioned that in the Gödel fragment, function symbols are not allowed, but individual constants are. Now, if phi is a sentence, Gödel fragment sentence, then it's clearly satisfiable over the same domains as is obtained by simply quantifying, simply replacing any constants with variables and existentially quantifying them. So I can get rid of constants just adding more existential quantifiers at the front, and of course that keeps me in the Gödel fragment because you're allowed as many existential quantifiers at the front as you want, so you can, as it were, de-scholemize the individual constants. So we can assume that there are no individual constants if we like. In fact, with a little additional work, we can eliminate both individual constants and leading existential quantifiers. So we have the following lemma. The satisfiability problem and also the finite satisfiability problem for the Gödel fragment here is reducible in polynomial time to the finite satisfiability problem or the satisfiability problem and the finite satisfiability problem respectively for the subfragment in which you have no leading existential quantifiers and there are no individual constants. So you can get rid of all these irritating leading existential quantifiers and constants and cope with and just deal with a simpler form formula. In fact, I shall not be proving this lemma. It's relatively routine and a little bit dull, so I'll just take that on trust for now. Okay, so next idea. In the absence of equality, elements can be freely duplicated. And this will be a handy trick in the proof that follows. So here's what I mean more precisely. Let A be any structure, fractor A, and let n be a positive integer. What we can then do is form the structure B, whose domain consists of the pairs of objects. The first element of the pair is simply an element of A, and the second element of the pair is an index between 0 and n minus 1. So you can think of these, the elements of B, as indexed elements of A, and they're indexed with numbers between 0 and n minus 1. And we turn that into a structure by declaring for any k-ary predicate R and any sequence of elements A1 to AK from A and any sequence of integers I1 to IK from the relevant index set, that B makes the n-tuple A1, I1, A2, I2 up to AK, IK satisfy the predicate R, just in case A1 up to AK satisfies the predicate R in A. In other words, the elements of B are these pairs, and a collection of pairs satisfies some predicate R just in case the first elements of those pairs satisfy R in the structure A. So effectively, these pairs are all copies. So the elements A1, I1, the various kinds of elements A1, I1, they're just copies of A1, and similarly for A2 and all the way up to AK. We're just copying elements. And we'll denote B as A multiplied by n. There we're just copying every element n times. And it's easy to show that if phi is an equality-free sentence of first-order logic over a purely relational signature, and A is a structure interpreting that signature, then A makes phi true if and only if the n-fold copy, the n-fold multiplication of A makes phi true. So you can't really tell the difference. As long as you've got no equality there, copying elements doesn't make any difference to anything. And you may, as a little exercise, want to try and write down a formula involving equality where this fails. So it's quite important that equality is not present. Now, we're now ready almost to develop a procedure for determining whether a given sentence in the Gödel fragment, or this subfragment of the Gödel fragment, without individual constants here, is satisfiable. As so often in these lectures, we'll be employing the apparatus of k-types. So remember that a k-type over a relational signature sigma is a maximal consistent of equality-free literals over sigma involving no variables other than x1 up to xk. So a k-type is literally a set of formulas. It's a finite set, and assuming that the signature is finite, which it always will be in these lectures, so we can, since it's a finite set, we can identify that set with its conjunction, and sometimes we'll think of a k-type as a single formula, just the conjunction of all the sentences in that set. And if A is a structure interpreting a k-type, then, and A bar equals A1 up to AK is a k-tuple of elements from that structure, then there is a unique k-type satisfied by A bar, and we'll denote that by type superscript fractor A for the structure, and then A bar in square brackets. So that just means the unique type satisfied by a tuple A bar, the k-tuple A bar in the structure fractor A. So we can think of a type as a description of a possible k-tuple in a structure. And there's another way of thinking of types, which we also met in the previous lecture. We can think of a type Tor as a little structure. And the domain of this structure is simply the elements x1 to xk. So we now think of x1 to xk not as variables, but as objects. And you might say, well, what relations do these objects satisfy in this structure? Well, we just look at the type. So if R is a predicate of arity, say M, and W bar is an m-tuple of these objects, x1 up to xk, we say that in the structure determined by the type, W bar satisfies R just in case the type contains the positive literal R of W. You see, a type is a set of literals, so it either contains this positive literal or it doesn't, in which case it would contain its negation. And if it does, we'll say that the relevant tuple of objects, because we're now thinking of variables as objects, satisfies the predicate R. So that's our notion of a type, and we think of types as structures. It sometimes helps to do things that way. Remember that a k-type Tor always features the variables x1 up to xk, and we'll think of it as a small structure. So now, if w bar is an m-tuple of variables, in other words, a word of length m over the alphabet x1 up to xk. So these are the variables in the type, or the objects of the domain, and w bar is a tuple of an m-tuple of these things. Then Tor applied to w with angle brackets will denote the m-type whose ith variable is a fresh copy of wi in the structure Tor. Now that's probably completely incomprehensible, but we can explain this notation quite easily with just a few examples, and I think you'll get the idea of how this works. So let's have a look at, so again, Tor, remember, is a k-type. So think of it as a structure, if you like, over the elements x1 up to xk, or a set of literals involving the variables x1 to xk. Tor angle brackets x1 denotes the literals of Tor featuring only x1. So because we have only one element here, we have a 1 type. And because it's a 1 type, it's a set of literals in the variable just x1. And which literals? Well, just the literals that are in Tor. Second example, Tor angle brackets x2. Again, because we have just one variable here, this will denote a 1 type. So it will be a set of literals in the variable x1. Which ones? There'll be those literals of Tor featuring only x2, but with x2 then renamed as x1. So it's a 1 type, but it's the 1 type of x2 in Tor. Next example, Tor x1, x3, x4, and so we have x1 and then a contiguous sequence from x3 to xk. So this has k minus 1 variables here, so it is a k minus 1 type, and it will therefore be a set of literals in the variables x1 to xk minus 1. Which ones? Well, it's the set of literals of Tor not featuring x2, because x2 doesn't occur anywhere here, but then we decrement the indices on x3 up to xk. So the second element of this type, the second variable of this type, x2, behaves like x3 does in Tor. The third variable of this type behaves like x4 does in Tor, and so on. And finally, final example. So what about Tor x1, x1, x3, and then a contiguous sequence up to xk? So notice what we duplicated x1 here. This has k positions, so it is a k-type. So it will be a set of variables, a set of literals, I beg your pardon, in the variables x1 up to xk. Which ones? Well, you ignore the variable x2, so you look at all the literals of Tor not featuring x2, because x2 doesn't occur here, and you then duplicate x1 and call the copy x2. So what does that actually mean? Well, if you want to know whether a literal is in this type here, substitute x2 by x1, replace x2 by x1, leave x1 alone, but replace x2 by x1, so you're duplicating x1, and then see if the resulting literal is in the original k-type Tor, and that determines your k-type. So it's still a k-type, but it's not the k-type we started with. It's a k-type in which x2 has been thrown away and x1 has been duplicated and called x2. So now let's just take a sentence of the Gödel fragment. I think we're ready to explain how the decision procedure works. All that technical apparatus, we should be in good shape. So here's a sentence, here's the fragment we're dealing with. Remember, we can ignore the leading existential quantifiers and any constants. Those can be got rid of by the lemma I stated a few slides ago. So the sentence looks like this: for all x1, for all x2, bunch of existential quantifiers, n variables in total, let's say, and we have a quantifier-free part, psi. So let's fix such a sentence and call it phi. What we'll do is we'll construct a certificate, fractor C, which has three components, R, S, and T. R is a set of 1 types, S is a set of 2 types, and T will be a set of n types consistent with psi. Psi is a formula, quantifier-free formula in the variables x1 to xn. So to say that an n type is consistent with psi is just the same as saying that that n type entails psi, of course. So we'll insist that C possess a collection of properties which I'll list on the next slide, and what I'm going to show is that phi is satisfiable if and only if a certificate C exists. Remember, C has to satisfy a collection of properties, and we need to construct or guess a certificate C. These will be finite objects, of course, and check that the relevant certificate has all the required properties. So that's our decision procedure. So here's the properties. I've called them C1 up to C5. And so remember, we'll go through these properties very briefly. Remember, as we're doing so, that C is a triple, a set of 1 types, so just a finite set of types. Types you can think of as just sets of literals, so a finite set of 1 types, a finite set of 2 types, and a finite set of n types. Each of the n types, by the way, entails psi. Of course, they're over the signature of phi, and they satisfy the following properties. First of all, if you take row 1 and row 2 in R, so these will have to be 1 types, of course, because that's what R is, then there exists a 2 type sigma in S, such that row 1 is given by the behaviour of the first variable in sigma, and row 2 is given by the behaviour of the second variable in sigma. So what that says basically is that any pair of 1 types in R can be extended consistently to a 2 type sigma in S. There's no requirement that row 1 and row 2 be distinct. Condition C2. This says that if you have a 2 type sigma in S, then that can be extended to an n type Tor in T. Right? So sigma is the projection of Tor just onto its first 2 variables. So ignore all literals in Tor other than those involving x1 and x2, involving any variables other than x1 and x2, and then that gives you this symbol here, and that's sigma. So any 2 type can be extended to an n type. Any 2 type in S can be extended to an n type in T. Third condition, for every 1 type row in R, there exists an n type Tor in T, such that row is the result of just looking at the first variable in Tor, and moreover, Tor is equal to Tor x1, x1, x3 up to xn. And this last condition may seem a bit puzzling, so what does it actually mean? So this expression here says, take x, if you want to know whether x2 satisfies something, then substitute x1, if you want to know whether a tuple of objects featuring x2 satisfies something, then substitute x1 for x2, so x2 now no longer occurs. Look to see whether that literal is true in Tor, and then that gives you your answer. So basically what this condition, and the condition requires that it gives you Tor. So this condition says that x2 behaves in Tor in exactly the same way as x1. It's indistinguishable from x1. It's like a copy of x1. Now, we don't say in the we don't say in the n-type Tor that x1 and x2 are the same or different. We can't do that. We don't have equality in types, sets of equality-free literals. However, we require that the behavior of x1 and x2 be consistent with there being x1 x being equal to x2. So they're essentially copies of each other. So that just says for any one type, there's an n-type in any one type row in R, there's an n-type tor in T, such that that n-type has the second element behaving as a copy of the first, and the first element of that one type behaves as required by row. And finally, the fifth, the fourth and fifth conditions are very easy. That they just say that if you've got an n-type in a tor in T, then take any position in that n-type, the behavior of the variable at that position is, well, that will determine a one type, and that one type will have to be in R. And finally, if you take any two positions, I and j, possibly equal, in either order, then the two type determined by their positions will have to be in S. That's all straightforward, I think. Okay, so we've got a bunch of conditions on the types. Of course, these are finite objects, so it's just a matter of checking. I mean, if we have a certificate or a potential certificate, we can check whether these conditions hold quite straightforwardly. So the easiest way to motivate these conditions is to prove a lemma, and this lemma will say that if the phi is satisfied in some structure, then we can build a certificate satisfying all these conditions, and this is done in the most natural way imaginable. So the lemma says if phi is satisfiable, it has a certificate. I mean, a certificate satisfying conditions C1 to C5. I think I've called them C6 here. I think there are just 5 of them. Should we check? It says there are just 5 of them here. So C1 to C5. Okay. So suppose, let's prove this lemma. Suppose that A models phi. Remember, phi is our sentence in this reduced Gödel fragment where we just have two universal quantifiers followed by some existential quantifiers, no individual constants. So if we have a model of this formula, what we'll do is we'll let B be the n-fold Cartesian product. In other words, we'll duplicate every element n times. And the reason we'll duplicate elements is that we want to talk about types of elements, and typically the types of tuples of elements. And when we talk about types of tuples of elements, we like these elements to be distinct, because then everything works a little bit better. So we'll just duplicate everything so that things are nice and distinct. So when I take a tuple of elements, occasionally I'll want to assign that tuple of elements a type. And it makes life very much easier when the tuple of elements is always distinct, because if they're not distinct, if there are duplicates in that tuple, then we're not always free to assign a type to that tuple of elements. So when I talk about the type possessed by a tuple of elements, I'll usually assume that the tuple of elements has no duplicates, all distinct elements. Okay, so let's have a look. We need to build our certificate first. So we've created this duplicate copy, this n-fold copy B of A. So the certificate has to have 3 parts: a set of 1 types, a set of 2 types, a set of n types. Which ones? Well, let R be the set of all 1 types realised in B, S be the set of all 2 types realised in B, and T be the set of all n types realised in B, which are consistent with psi. Psi, remember, is the quantifier-free part of our formula phi. And what we'll do is we'll check that C satisfies the condition C1 to C5, as it turns out. So let's have a look. So I'm not going to go through them all because that will take a long time. Let's just go through a few of them. So here's C1. Condition C1 says that for every pair of 1 types, row 1 and row 2 in R, there exists a 2 type sigma in S, such that row 1 is the behaviour of the first variable in sigma, and row 2 the behaviour of the second variable in sigma. Well, that's easy. If row 1 and row 2 are in R, then we can choose distinct elements, B1 and B2, realising this one type. B distinct because we've got plenty of duplicates in B. And so, so even if row 1 equals row 2, we can choose B1 and B2 distinct. Have a look at their 2 type, and there we are. You've got it, right? So the 2 type B1, B2 will be realised in S, because that's the way R and S are defined, and so we have condition C1 holding. Let's just do one more. Condition C2 says for every 2 type sigma in S, there exists an n-type Tor in T, such that sigma is given by the behaviour of the first 2 variables in Tor. Okay, so let's see why that's true. Well, if sigma's in S, then by the definition of S, right, S is the set of 2 types realised in B, well, there must be elements, B1 and B2, realising sigma in B, distinct elements. Remember, when we take things to realise types, we'll always just assume that they're distinct. So there must be distinct elements, B1, B2, realising sigma in B. So we pick B, we then well, let's think about what's going on here. B is a model of our formula phi. And what does the formula phi says? It says for all x1, for all x2, there exist x3 up to xn satisfying psi. So, since we've got B1 and B2, which are elements, well, I'll just put that in the formula, and we know that there exist elements B1 up to Bn, such that the tuple B bar given by B1 up to Bn satisfies psi. Moreover, we can assume that these are distinct, because B has so many copies of everything, we can just take them all distinct. So we then, and of course we know that B satisfies psi, so let Tor be the n-type of B bar. Well, what is T? T is the set of n-types realised in B consistent with psi. Well, that will include B bar. So condition C2 holds. For every 2 type sigma in S, there exists an n-type T in Tor such that sigma is given by the behaviour of the first 2 elements of Tor. Okay, so, and the rest, the other conditions are similar. So those are the conditions. Now, we've shown that if a formula is satisfiable, the formula of this Gödel fragment, this subset of the Gödel fragment, is satisfiable, then it has a certificate. We now got to show the converse. If a formula has a certificate, it's satisfiable. And to do that, we need to suppose we have a certificate and then build a model. We need a couple of technical devices for this, and I suppose the most important is a pairing function. Okay, so we're now going to show that the existence of a certificate for phi guarantees that phi is satisfiable. So we'll employ as a technical device a bijective function which maps pairs of positive integers. I'll use n plus for the positive integers. Pairs of positive integers to the positive integers. There are lots of pairing functions. Here is one. Any one will do. The point about these pairing functions is that they are bijective, and you'll see that I've numbered the variables. The columns of this square represent the values of the variable x starting at 1, the rows the variable y starting at 1, and I've written in the relevant square for xy the value of the function pi xy. And you'll see just from this example, it goes 1, 2, 3, 4, 5, 6, 7, 8, 9. And in fact, we list, every integer, every positive integer occurs in that sequence exactly once. So this is a bijection, the familiar bijections between pairs of positive integers and positive integers. Because it's a bijection, of course it has an inverse. So for each positive integer k, there are functions pi1 and pi2 such that the pair pi1 of k and pi2 k give you the numbers x and y such that pi of x and y is equal to k. They're just the inverses. And so what have we got here as an example? We take the k equals 14, pi1 of 14 is 2, so the x-coordinate is 2 here, and pi 2 of 14 is 4, so the y-coordinate is 4, 1, 2, 3, 4, and that's exactly that square there. So and if you want to amuse yourself with a bit of algebra, you can derive expressions for pi 1 and pi 2 if you like, just a little exercise, but you can clearly do it. So, for every pair of positive integers I and j, the number k equals pi ij satisfies pi 1k equals I and pi 2k equals j. So they're just inverses in the obvious sense. By the way, you can also easily check that pi 1 of k is less than or equal to k, and pi 2 of k is also less than or equal to k. I mean, you can verify that empirically with these examples here, but you can show it as well. Okay, so that's the pairing idea. Now, suppose that we have a certificate for phi. How do we define a model? The way we're going to define a model is by taking a sequence of k-types, where k is a positive integer. So there'll be a 1 type, a 2 type, a 3 type, a 4 type, and this will go on forever. So an infinite series of k-types. Now, I'm sorry, an infinite series of types. And I'll call these types zeta 1, zeta 2, and so on. So I'll use zeta for these types. I haven't told you what they are yet. I'm going to construct them. Now, a very important point about these types is their arities. Their arities will increase, but they won't increase by 1. They'll increase at every stage by n minus 2. And so the arity of zeta k will be given by the function a of k, and that's this function here. 1 plus k minus 1 into n minus 2. So if you do the sums, you will see that a of 1 is 1, and a of k plus 1 is always n minus 2 greater than a of k. So they just increases by n minus 2. And so a of k, remember, will be the arity of zeta k, the kth type in our sequence. Okay, now, again, I haven't told you what the zetas are, but I'm going to. Now, when I define them, I will make sure that to maintain these invariants. So for all k, when I define my types, I will make sure that these invariants hold. And I'll just go through the invariants quickly. Details are hard to keep in mind, but need to get an idea of what's going on here. So the first invariant says that if k is greater than 1, then zeta k extends zeta k minus 1. So why does it say that? Well, the arity, remember, of zeta k minus 1 is a of k minus 1. So if you take the first a of k minus 1 variables of zeta k, that gives you exactly zeta k minus 1. So that condition simply says that zeta k extends zeta k minus 1. It agrees on the variables occurring in zeta k minus 1 and says something more about the additional variables. Okay, next invariant. For k greater than 1, this is a bit funny. So if the psi will hold. Remember, psi is the quantifier-free part of our formula phi. The formula phi says for all x1, for all x2, there's a bunch of things, x3 up to xn, satisfying psi. And this invariant will say the following. Psi is satisfied. So in the type zeta k, psi will be satisfied by the n-tuple whose first two elements are pi 1 of k and pi 2 of k, and whose remaining elements are the final variables occurring in zeta k. So the variables of zeta k start at x1 and finish up at xa of k. And this tuple of variables here gives you exactly n minus 2 variables, and these will be the new variables occurring in zeta k that didn't occur in zeta k minus 1. And so it says that if you take x pi 1 of k and then x pi 2 of k, and then complete with the final variables, then that tuple of variables will, according to the type zeta k, satisfy psi. So there are n variables here in total. Okay, so this is a little bit tricky, but you've got to remember that pi 1 of k simply identifies pi 1 of k is just a number between 1 and k. So it's certainly one of the variables in zeta k, and pi 2 of k is the same. So we have two variables here, which are variables in these are just variables in between x1 and the last variable in xa of k, is the last variable occurring in zeta k, and this collection of variables satisfies psi. Okay, so the next two conditions just say that if you take the ith variable of zeta k, then the one type of that variable has to be in the certificate R, and if you take any two variables, then the two type they define will have to be in the set S. Remember, R and S occur in our certificate, and they are just sets of one types and two types respectively. Okay, so those are the invariants we'll maintain. So I've now got to define my sequence of variables. Okay, we'll start with k equals 1. I'm sorry, I've now got to define my sequence of types, zeta k. Start with k equals 1. So a of 1 is 1, so I need to define a 1 type. How do I define a 1 type? That's easy. I'll pick any row in R and I'll set zeta 1 equals row. So that gives me a 1 type. We're fine. Done. So that's easy. I got my 1 type, and we need to check that these invariants hold. So we've got the various invariants. Well, the first two invariants only apply when k is greater than 1, so I've grayed them out. They don't really, nothing to check. The last two invariants, the requirement is that every variable of zeta k, in this case k is 1, remember, so xi can only be 1 here. So the variable xi1, the 1 type determined by the first variable of the only variable of zeta 1 has to be in R. Well, it is by definition because that's how I picked it. And this last type says that if you take any two variables, the two type that they define is in S. Why is that true? Well, because the 1 type determined, the two variables have to be the same in this case, because if k equals 1, the only possibilities for I and j are I equals 1 and j equals 1. And so the 1 type determined by this thing, which is just row, is in R. So row is in R and row is in R. And condition C1 on certificate says that there exists sigma with the required properties, and that everything's fine. Okay, so the invariants hold for if you take as your initial zeta 1 just any 1 type in R. Okay, so now we've got to do the work. Suppose that zeta k is defined, and this will have arity a of k. They're quite a large number in general. Okay, so what we're going to do is build zeta k plus 1. So the first thing we need to do is we need to identify the indices I sub k and j sub k. And these will be given by pi 1 of k and pi 2 of k. Remember what pi 1 and pi 2 are? These are the inverses of our function pi, which maps the positive integer square to the positive integers bijectively. So this is effectively k. Any positive integer k represents a pair of integers, and pi 1 and pi 2 give you the decoding, so they tell you which pair of integers k represents. Okay, so I'll just to avoid writing lots of functions which are hard to say, I'll just call these call these indices ik and jk, and we identify them. They'll be somewhere in here. Okay, definitely there'll be indices within the required range. In fact, they'll be less than k, less than or equal to k, and so certainly within the required range of between 1 and ak. Okay, so let's suppose for the moment, just for definiteness, that xik and xjk are different. I mean, they could be the same, but the reasoning in the case where they're the same is similar. So I'll just deal with the case where these things are different. What we need to do is to construct additional elements to define zeta k plus 1. So the yellow stuff here is defined already. We're going to define zeta k plus 1. Now this blue stuff, really these elements here, will be the extra elements, the extra variables featured in zeta k plus 1. So these will range, their indices will range from a of k plus 1 all the way up to a of k plus 1. So we're going to, we need to, so those will be the extra elements, so I'll need to define a type on these. So the first thing I will do is I'll take these elements, xik and xjk. Remember, these represent the pair of elements encoded by k, the pair of indices encoded by k. And what I will do is I will say, right, okay, these elements, right, satisfy some 2 type in the structure zeta k, in the yellow structure that we already have, and by the condition on certificates. So of course that certificate, that sigma has to be, that 2 type has to be in S, the set of 2 types in the certificate. That's a condition. That's one of the invariants that we are maintaining. So if we take the 2 type of xik and xjk, that will have to be some 2 type sigma which is in S. That's an invariant on the zetas that we're maintaining. And by the condition on C2 on certificates, there exists a Tor in T such that sigma is simply the projection of Tor onto its first 2 elements. So what we'll then do is we'll define the n-type featuring xik, xjk and these fresh elements to be Tor. Remember that these are all distinct, so it's legitimate to simply assign these any n-type we like. There are n-2 new variables. We've got a 2 type here. So that's n-type. And notice that because we've chosen Tor from T, the tuple consisting of this element, that element, and the new element will satisfy psi. That's the idea. So we found witnesses now for this pair of elements. Okay, so we can clearly define we define this n-type freshly. I mean, we certainly won't conflict with the 2 type already defined here. And so that gives us a partial definition of this larger type zeta k plus 1, the yellow stuff and the blue stuff. This is going to be zeta k plus 1. Now we need to complete the definition of zeta k plus 1 because we haven't specified all of the relations in this definition. We've just specified what we know about zeta k and this n-type here. That's by no means the whole of it. Okay, so the next thing we do, we have to complete this. So how do we complete this to be the zeta k plus 1? Okay, so let's take any pair of variables, any pair of objects whose 2 type we haven't yet set. Just for definiteness, I'll assume that the first variable xi occurs is one of the variables of zeta k, and the second variable xj is one of the variables of x, one of the variables xj, and one of the new variables, and I'll assume that I don't think we really need to assume anything here, that this is something which hasn't been defined yet. So we'll have a variable here, xi, which is in the variable in the type zeta k, and a new variable. What two type should we assume for this? Okay, well, this variable here will have a one type, and that one type, let's say call it row 1, will have to be in the set R, in our certificate R. Why? Because that's one of the invariants we're maintaining on the types zeta k. What about the one type here, x, the one type of this variable? Well, this one type will be determined by the n type that we've just assigned, the blue n type. But it's a condition on certificates that if we look at the one types, any of the one types determined by an n type in T, then that one type will be in R. So this one type will be in R as well. Furthermore, it's a condition on certificates that we can find a 2 type in S, and we'll assign that's consistent with, let's say, row 1 and row 2, these one types, and we'll assign this 2 type accordingly. So we assign any 2 type that hasn't been assigned yet in that way. Okay, so that's defined the structure a little bit more. It hasn't completely done everything. So there may still be some unassigned tuples, and we'll just assign them arbitrarily. We'll just, if we have some tuple, let's say some 15 tuple that we haven't assigned here, we just assign it arbitrarily. We've done enough at this point. So we've assigned this n type, the blue material, and for each pair of variables where the 2 type hasn't yet been defined, we'll assign a 2 type using the certificates in the way I just described, and that 2 type will always be in S. And so if we in that way we've constructed our new type zeta k plus 1. So this whole thing will be called zeta k plus 1. I've shown you how to construct zeta k plus 1, and it's routine to check that the required invariants hold. Okay, so now we can go on. Having constructed zeta k plus 1 from zeta k, we just keep going. So each a of k type zeta k can be regarded as a little structure over the elements x1 up to x a of k. And remembering the invariant, which says that the kth type is consistent with the k minus 1th, the type zeta k, the kth type in our series is consistent with the k minus 1 type, k minus 1th type. In other words, it just extends it. What we can do is define in a natural way a limit, and that gives us a countably infinite structure. We'll call that fractor x over the domain x1, x2, x3, all the way up to infinity. So that gives us a nice infinite structure, and this is the structure x which we'll be working with. Okay, so our structure x. So we've defined a structure x using this sequence of consistent types, each of arity a of k. This keeps growing. Now I claim that x is a model of phi. And the reason that x is a model of phi is that if you consider a pair, take any pair of objects in this structure, because it's a pair of objects, I mean these objects will be xi and xj, and there will be a k such that I is pi 1 of a k and j is pi 2 of k. There will be some such k, just because we're dealing here with a bijection between the positive integers and pairs of positive integers. So choose such a k. Well, when we defined the type zeta k plus 1, we were careful to make these new elements of the type zeta k plus 1 be witnesses for psi with respect to the elements x pi 1 of k and x pi 2 of k. In other words, everything got witnesses. So because everything got witnesses, phi, which just says that any pair of objects has to have some witnesses satisfying psi, well, that will be true. So we have now constructed a model of phi on the assumption that phi has a certificate. So remember, this is what the formula phi says. For all x1, for all x2, there exist a bunch of things satisfying psi. Well, that must be true, because any objects x1 and x2 will have to have the form x pi 1 of k and x pi 2 of k for some k. And then when we define zeta k plus 1, they'll get the witnesses. Okay. So, what have we shown? A sentence of phi of the Gödel fragment is satisfiable if and only if it has a certificate C. Since C is bounded in the size of phi, the latter condition can be guessed and checked. So clearly the satisfiability problem for the Gödel fragment is decidable. Now you might wonder about complexity, and here you do have to be a little bit careful, because when considering n-types, since there's no bound on the arity of predicates, the number of n-types can turn out to be doubly exponential. So we have to be a little bit careful here to keep things within reasonable bounds. When considering n-types, we don't care about, and for any n, we don't care about literals that are not substitution instances of literals in phi. These can't make any difference to the truth value of phi. So what we can do is look at all the literals in phi, look at all the substitution instances of those literals, and when constructing types, or sets of types, when constructing types, we can just choose the truth values of, you can choose whether the literals in the type are positive or negative, assuming that those types, assuming that those literals are substitution instances of atoms occurring in phi, and then we can just make all the other literals false. So when you simplify things in this way, when you ignore, as it were, irrelevant literals, it turns out that the number of types is only exponential as a function of the size of phi. You can check that in detail yourselves. So that means, therefore, that certificates are of exponential size as a function of the size of phi, and that means that the satisfiability problem for determining the satisfiability problem for the Gödel fragment is in NExpTime. What about the matching lower bound? Well, we've already pointed out that the subfragment of first order of the two variable fragments in which there's no equality can be reduced in logarithmic space to the Gödel fragment, and we showed in a previous lecture that this the former fragment is NExpTime hard, and it follows, of course, that the Gödel fragment is itself NExpTime hard, because there's a reduction from a known NExpTime hard a fragment, the known NExpTime hard satisfiability problem, namely Gödel, the two variable fragment without equality. So we have a matching lower bound in this case as well. So we've proved that the satisfiability problem for the Gödel fragment is NExpTime complete. Let me finish with a few historical notes. Notice that the model X we constructed in the above proof is infinite. With some more work, we can in fact construct a finite model of phi from a certificate, and that shows that the Gödel fragment in fact has the finite model property. In other words, the satisfiability problem and finite satisfiability problems coincide. And Gödel provided just such a construction in his paper of 1933. The simpler construction that we described is due to Laszlo Kalmar, same year. The last sentence of Gödel's paper famously claims that the construction is unaffected if you add equality. This is not correct. It turns out that the Gödel fragment with equality, sometimes called the Goldfarb fragment, is undecidable for satisfiability and finite satisfiability, and that was shown in 1985.